Yeah, so I want to thank the organizers, first of all, for an incredible conference. I think the selection of speakers has been really, really amazing, and also the relevance that everyone has had to everyone else has been great. I've learned a ton. And I really appreciate the chance to tell you a little bit about my work here. So thank you very much for the invitation to speak. So I'll be talking about measurement-based control, and specifically focusing on some of these open quantum systems approaches that we've heard about in a lot of the other talks. So the general motivation for this kind of thing is that measurement is very different in quantum mechanics, as we all know. So in the context of control, if you want to do some kind of feedback scheme, measurement's really only telling you how to optimize the use of your controls. Like if you're trying to stabilize the temperature of a room, you don't measure to change the temperature of the room, you just measure to figure out how to use your heater to change it. On the other hand, in quantum mechanics, there's many ways to divide it up, but there's at least sort of two very fundamental distinctions. One is the way that you measure is very important for the information that you acquire. So there's multiple informationally complete ways to measure your system. And consequently, like if you want to do something crazy like measure the phase of this cat state, you better make sure that you don't have a measurement apparatus that's sensitive to whether or not it's dead or alive. And then in the context of control, you want to make sure, well, you have this additional resource now. So the fact that measurement disturbs your state can actually be a benefit rather than a detriment. And if you have the superposition state, you can actually collapse it randomly into being one state or the other. So there's a physical change in the system, even if your system is in a known state, which is truly quantum phenomena. OK, so in this talk, I'm not just going to focus on measurement, but specifically on continuous measurement. Because I think this is really a situation in which, sort of when you're looking at your measurement process in the most fine-grained way possible. So the important thing to realize is that any realistic measurement involves an interaction with another system. And that interaction has some finite timescale associated with it. So there's really no such thing as an instantaneous projection like we learned about in undergraduate quantum mechanics. So for example, if I have some laser and I have an atom interacting with that laser, if after some finite amount of time, because this interaction strength between the atom and the electromagnetic field is finite, the system will never instantaneously go to an eigenstate. And what this means is that your detector only learns a finite amount of information over any finite time interval. The reason we don't learn about this in undergraduate quantum mechanics is because by the time our detector has acquired enough information to know something sort of infinitesimal about our state, the environment has already learned far more than we have. So in this case, by the time your detector actually clicks, any sort of intermediate evolution that happens before that click has been washed out by the fact that the environment got a click somewhere. But recently, technologies are developed where you can really get really high efficiency quantum measurements. And this allows you basically to use and observe these intermediate states. And then this allows you to do feedback. So now, feedback is not just about projecting and then doing some operation conditional on the measurement outcome. It's more about acquiring information continuously and then adapting to this sort of finite amount of back action. So the main kind of questions that I want to ask in my talk are what sort of fundamental advantages do you get from viewing measurement back action in this way and doing feedback in this way, where you update your system and then act on your system while it's being measured. So the first part of my talk will just be talking about measurement back action. I want to just give a sense of sort of the scope in which these kinds of models are relevant. Then I'll have an experimental part of my talk where I'm talking about how to implement an ideal phase measurement using adaptive measurement. So that's going to use this notion of continuous measurement. And in the second half, I'll talk more on the theory side about first a general method for deriving measurement-based feedback protocols, and then showing some applications of that formalism to entanglement generation. So to move on to the first part, just talk about back action. To give a slightly more detailed explanation of weak measurements. So we've already heard sort of a nice analogy in Younghan's talk of the Stern-Gerlach experiment, which I think is a nice classic example of what a weak measurement is. So if you have a spin and it has a continuous degree of freedom, like its momentum, if you pass that through a magnetic field gradient, then you'll get a phase, a displacement in the position conditional on the internal state. And because of the Heisenberg uncertainty principle, the spin necessarily has some intrinsic uncertainty in its momentum, which means that the distribution of the positions on the screen has an uncertainty that is not just due to imperfection of your detectors. And so when you measure the position of this, conditional on the internal spin state of your atom, you'll get sort of this distribution or this distribution. Now, if you measure one of the extremes, if your position happens to come way down here, then it's far more likely that your spin was in this blue state than in the red state. And so that the back action on your spin is going to project you into this ground state. If your measurement outcome is very high here, then you're pretty sure you collapsed into this red state, and so you project up here. But the interesting thing in weak measurement is what happens when your measurement is indeterminate. So if you get a measurement outcome here, there's no way that you can tell for sure what state your system was in, because both outcomes were possible. And because nothing else in the universe could possibly know about the state of your spin either, it hasn't interacted with anything else, then your system remains pure just by unitarity. And so in general, you have this more general form of back action than just projective measurements, and your state doesn't just go to an eigenstate. So you might say, okay, well, that's kind of a contrived example. That doesn't look like anything I have in my lab. Well, again, we have, the reality is that for most, if not all, measurement devices, there's some kind of time scale associated with your system's interaction with that device. And therefore, you're going to have a similar kind of interaction. So for example, if I have some completely general system, a common way to model these is to say that it's interacting with a bath. So you might think of this more in the context of decoherence, but a measurement apparatus can be often modeled in this way as well. And then if sort of a single degree of freedom from this bath comes over, interacts with your system, and then goes back, then that's going to perform a tiny measurement of your system due to the entanglement of this interaction. And if you have, if you then measure the degree of freedom of your bath, then you've acquired a tiny amount of information, which is manifest as a tiny separation of these histograms. But because of the intrinsic uncertainty of the degree of freedom of your bath, there's this wider distribution. This is one way to model these baths that tends to be accurate when you're measuring the continuous degree of freedom here. So if the intrinsic uncertainty here is much greater than the information acquired, then you can model this with a stochastic differential equation. So now the measurement outcome is a stochastic random variable, dominated by the noise, but with a small amount of information gain. And if you take sort of this operator from the previous slide and plug all these things in, you derive, well, first of all, you do this many times, first of all, to get a continuous measurement interaction. And then you end up deriving a stochastic differential equation, which we've seen in many of the talks over the course of this conference, where this first term is familiar to anybody who considers just open quantum systems. This is the term you get just having your system interacting with a bath, so it's your familiar Lindblad dissipator. But then you have this second term due to innovation, the fact that you actually measure your bath. And this is the term that will actually take you toward an eigenstate of your measurement outcome. All right, so moving on. So now that we have this formalism, how do we use it? What new advantages can we get from thinking about measurement in this way? To give a slightly more concrete example, our system is going to be an atom interacting with the electromagnetic field. So a way that we can think of an atom interacting with a field in the context of weak measurement is if you imagine that the electromagnetic field is decomposed in this infinite set of modes that are localized in time. Initially, they're in the vacuum. So suppose your atom is in sort of a one-dimensional setting. So these modes come in and they interact one by one with your atom. Then at a small infinitesimal time step, one of these modes comes and interacts, and there's a bit of entanglement now between your atom and this electromagnetic mode. And when you measure that mode, that creates this stochastic backaction term. So in the context of adaptive measurement, why should we care about this? Well, now that not only have we learned something about the state, but we've actually disturbed the true state that we were trying to measure. There's some intrinsic backaction here. And therefore, the optimal measurement basis to learn about some particular quantity may now not be best measured by the original measurement operator that you chose. So you may be better off as you disturb your system to change your measurement apparatus, and then you change your state, and then you just repeat this process. So sort of the general question that you would ask is, what new kinds of measurements can you implement when you allow this more general formalism of having your measurement operator depend not only on time, but also on the previous measurement outcomes? So there's many known examples of this, some of which have already been demonstrated experimentally. First of all, there's the famous Dolinar receiver, which allows you to optimally distinguish coherent states. There's some ways that you can use adaptive measurement for state control, so you can actually stabilize a discrete set of states of a qubit just by changing your measurement basis. Also, another way you can use this for control is the scheme, in fact, I'll talk about today, allows you to deterministically prepare single rail photonic qubit states in an arbitrary state. which is an important problem for single rail photonic computing. And then the thing I'll talk about today is that when you do these adaptive measurements, you can perform a better measurement of phase using linear optics than you could just with that adaptive measurement. So what's the motivation for measuring phase? Well, we don't have a perfect device that can measure phase currently. So to contrast this with other things, if you want to measure the power of an electromagnetic field, in principle, you can build a device, photon counter, that measures exactly in this basis. You just project into photon number states. If you want to measure amplitude, like X or P or these quadrature operators, if you're thinking about the electromagnetic field, then you can do HOMODYNE detection or heterodyne detection, and that, in principle, can do a perfect measurement in this basis. But if you want to measure phase, which you would define as this, so there's no operator you can write down corresponding to phase, but there's nevertheless a measurement basis that you can project into. There's not really a device that exists that can do a projective measurement in this basis. So that's the problem that we want to consider here. The interesting thing about this basis is it contains a uniform superposition over all photon number states. So a measurement outcome in this basis doesn't tell you anything about the power of your signal. So in that sense, it's canonically conjugate to photon number. And so what does it mean to build a device that measures in this basis? It just means I have a device that spits out a classical number theta, where the probability of a measurement outcome theta occurring, given you input some state rho, is just given by the Born rule, where you define the theta states as such. And now to contrast this with some other stuff, so Howard, for example, on Wednesday talked about doing Heisenberg-limited measurements of phase. So in this case, we're just saying you're given a single copy of the state that you want to measure the phases as well as possible. So there's no notion of sort of using multiple passes, say through an interferometer, to sort of build up coherently your phase and measure it more efficiently. And also there's no notion of using entangled inputs to enhance your performance, because you just have a single copy of the state. You don't have the freedom to prepare a more entangled state than what you're given. So adaptive measurement is the only resource that's left to you of the three that were mentioned previously. Now you might say, okay, well, everybody measures phase. Don't tell me I can't measure phase. And of course, you're right that there are many techniques that do a pretty good job at measuring phase. I'd say the standard is heterodyne detection. And that's essentially an amplitude measurement, measuring in one of this basis or this basis, where you rapidly rotate that measurement basis in time. And that implements an approximate canonical phase measurement, but it still acquires undesired amplitude information. Now, people have tried to go beyond this, and there are a number of really interesting works that have. So there was some work by Mabuchi in 2002 where they used adaptive measurement to try to better discriminate coherent states. And this gets a little bit better than heterodyne measurement and closer to the quantum limit. And then also there's plenty of works on trying to achieve Heisenberg-limited scaling and using adaptive measurement in that context as well, like Howard talked about. These schemes tend to perform worse at low photon numbers, which is particularly important when you have a state, an input state where the uncertainty is dominated by quantum uncertainty, which is where you really think you might be able to get a quantum advantage and where quantum mechanics comes into play. So the aims of this experimental work are first to perform a canonical phase measurement at the single photon level, and second to use the notion of quantum trajectories and continuous measurement to actually verify the device and see that we are indeed implementing a canonical phase measurement. So the experimental apparatus in abstract terms is built up from a transmitter and a receiver. The transmitter consists of a single atom, which we're going to use to emit a single photon. We'll prepare it in a superposition of its ground and excited states, and then have it spontaneously emit a superposition of 0 and 1 photons, where the phase is preserved from the dipole moment of this atom. And our goal is to estimate that phase as best as we can with this receiver. So the receiver receives the photon, and it's going to be, again, an amplitude measurement or a HOMODYNE measurement system, essentially, where we're going to be able to change that measurement basis in time. So to contrast with the sort of existing standard methods, if you were to just keep that phase, that measurement basis phase fixed as a function of time, that's HOMODYNE detection, and the intrinsic efficiency with which you measure the phase of your system is 80%. If you start rotating this measurement basis rapidly in time, large compared to the time scale of this photon, then your efficiency goes up to 89%. And let's think for a minute about why that is, because there's a nice intuitive reason for this. So if you start out measuring, you just pick a random axis, supposing that you have no initial information about your phase, and you acquire, so a small amount of this photon hits your detector. Now you acquire a little bit of information about what the phase is. And so now your best estimate is either aligned or anti-aligned with the measurement axis, depending on if the measurement outcome from your detector was positive or negative. And now at this point, if you were to continue measuring in this basis, you're going to essentially be inquiring information about the length of this vector, which is acquiring amplitude information. And amplitude doesn't commute with phase, and so that's actually not going to be optimal. So the best thing you can do is to rotate your measurement basis to be orthogonal to your best estimate of the state. And now intuitively, the reason this is good is because you're not really sensitive to the length of the vector anymore to first order. But if your best guess was actually off, so in this case, the true state is this green arrow, then most likely you're going to get a positive fluctuation here, which is going to tell you something about how your guess of that angle was wrong. And now if you continue to try to maintain this condition where your measurement axis is orthogonal to your best estimate of the state as the photon arrives at the detector, then in principle this can implement a 100% efficient measurement of the phase. So that's a canonical phase measurement that we're after. So the experimental system we have for doing this, we're working with superconducting circuits. So we have basically the simplest qubit you can make in these systems right now, a transmon qubit in a 3D cavity. And that's how we're going to prepare this dipole moment. We have this qubit spontaneously emit that excitation into a one-dimensional transmission line. That goes into a Josephson parametric amplifier. So this is another way of doing HOMODYNE detection, essentially. It's a single-mode squeezer. So the output field looks kind of like this. There's some anti-squeezing and some squeezing. And so you erase information about one quadrature. You amplify it about another. And then you feed that information back. We're using a field programmable gate array to estimate information based on this measurement outcome and then change the squeezing axis of this amplifier. Now, an important thing about this is there's some time scale associated with this feedback, right? So it takes about 360 nanoseconds to go from a bit of this photon hitting our detector to getting that information, processing it, and then changing our measurement basis. And that's not a good thing because if you acquire some information, we know that the best thing to do is to change your measurement basis. But you have this dead time. So how do we ameliorate that? Turns out that if you shape your photon, you can do a lot better. So what we're going to do is instead of just using the direct spontaneous emission of our qubit, we're going to do this sideband cooling scheme. So what we're going to do is we have this qubit in a cavity. We Rabi drive it at some fast frequency, so we get some effective dress states, plus and minus. And there's some splitting here. If you then apply sideband to the cavity, not at cavity resonance frequency, but detuned by the Rabi frequency, then you're going to drive this transition. So you'll go from the plus state, the one dress state of that Rabi drive, in 0 excitations in the cavity. It starts in the vacuum. And you drive to this minus state with 1 excitation in the cavity. The cavity's open, so it's going to quickly decay and emit that photon while leaving your atom state unchanged. And now this drive isn't resonant with anything. So essentially, you have an irreversible decay from the plus state to the minus state where the cavity emits a photon. And that's essentially spontaneous emission. It's the same physics. But now we can change the amplitude of the sideband, and we can change the cooling rate, which means that we can change the shape of our photon. So if you had this cooling rate be constant as a function of time, you get this familiar exponential decay of your photon. But if you do the right thing and you change the amplitude while you're decaying, you can actually make a flat photon. So here is a nice situation where the amount of measurement that you gain in every time step is roughly the same. So you're going to actually be a lot more robust to feedback delay, where if you'd used an exponential photon, you'd learn most of the phase in that first time step, and feedback wouldn't help you nearly as much. And this was essential to getting this experiment to work. So now that we have that system up and running, we can start to measure the back action. So the experimental sequence is we're first going to prepare our qubit in its excited state. We cool for some amount of time less than the total time it takes for the atom to decay to the ground state. And then we have the luxury of being able to perform tomography on our atom so that we can see what's the state after this cooling process. And if we look at the measurement outcome during that cooling time, we look at the output of our amplifier, and then condition our tomography results on that outcome, then we can actually see what the back action is. So if my measurement axis is just fixed, I'm not doing any heterodyne or rotation of that measurement axis, you can see that the back action always lies in this plane. So that means that the system is, it's never kicked outside of this plane because you never learn any information about that operator. And you're only going to end up being disturbed along the phase that you measured. And then if I change that phase by pi over 4, then instead I'm kicked in this axis. So we can verify that we can control the back action and measure and see that it's actually changed as we expect. If we switch to heterodyne detection, so instead we rotate that measurement axis rapidly in time, then to contrast, instead of the trajectories evolving in a fixed plane of the Bloch sphere, now it explores the entire Bloch sphere. And so now you're doing better in principle than HOMODYNE detection, because at least sometimes your measurement axis is orthogonal to that state. But it's not as good as you can hope to expect. So one more thing before I go on to the feedback is to think about what happens when your measurement axis is in the good state or the bad state. So the good state or the bad state is when you're aligned with your best estimate. And that's the case when your unconditional qubit state, or your conditional qubit state, not knowing the initial state, is aligned here. And so that's going to cause measurement back action along the z-axis. So everything you learn is basically going to kick your qubit up and down, and it's going to tell you that undesired amplitude information. Whereas if you manage to maintain this orthogonality condition, then the back action isn't any longer in this vertical direction, it's in the phase. And so that means that if you look at the dynamics of your transmitter, because of the entanglement between the transmitter and the photon that it emits, you can actually learn something about how well your receiver is performing. So if you have phase back action, that means that you're doing the right thing, essentially. So now we're in a place to start looking at that back action. So I'm going to show you a video of some experimental data where the red line is that measurement axis. As we measure, we gain information about the state. So first we know nothing, but we learn something, and the state vector grows. Now the measurement disturbs the state, so it gets kicked around. But as you learn that information, the feedback controller is going to change the measurement basis to try to track the state. So you see it's kind of trying to keep yourself orthogonal. And the interesting thing from the perspective of back action is that if you look at how much your system is disturbed in the vertical direction, you're getting a little bit less noise. It's a bit hard to see with the color scheme here, but you're getting a little bit less noise. So dz tends to be smaller when you do adapting than when you do heterodyne detection. So that's a sign that you're not learning amplitude information. And then what's, I think, much more striking is if you look at the phase back action, then the sort of the magnitude of d phi here, so the amount that your state's phase is getting kicked, is on average much, much larger when you do adaptive detection than when you do heterodyne detection. There's this very sharp line here around 0, which is a sign that you weren't measuring phase. So that's not a good thing. If you look at sort of the ensemble of the trajectories, we can look again at heterodyne detection. Apology for the sort of rougher quality of these plots, but we're basically just looking from down the pole of the Bloch sphere, preparing in the excited state as a function of time. And what's hard to see from these plots, but I pulled this figure from a really nice paper by Benjamin Ward. This was also talked about in Elaine's talk. The system tends to evolve in a spherical shell, and so it spreads out uniformly along here to the ground state, and that's what's happening in these plots. If we contrast that with adaptive detection, you notice that there's kind of this hole opening up. And what that means is that you're not actually evolving just in a sphere anymore, but you're actually evolving in a ring, concentrated in a specific state, which is a sign that there's no randomness. So if you started a known state, you're just going to continue to evolve deterministically in the z direction, and all the randomness is in this phi direction. So that's again a sign that your back action, you're only learning about phase information. And this is really sort of an unambiguous sign that you're doing much, much closer to a canonical phase measurement. So you say, okay, they're nice trajectories, but show me the money. How is this really doing better than standard techniques? So what we do to actually infer the phase from all these measurements is we compute this quantity here, which is pretty intuitive. We're just going to take the measurement record from our amplifier. We're going to multiply it by a complex phase factor associated with the measurement basis, and then also weight it by the mode shape of our photon. So this is just going to be constant, roughly constant for the photon that we generated. If we compute the complex argument of that number, that gives us the best estimate of the phase that the photon had. We can plot a histogram of that. So if I prepare my photon to have 0 phase, then this distribution is peaked at 0. And the magic comes when you look at the variance of this distribution. So how noisy is this? If you do heterodyne detection, we're going to use the Holevo variance, which is just a generalization of variance for a periodic function. And if you look at the variance for heterodyne detection, it's substantially higher. We can, from the heterodyne detection, infer not only what HOMODYNE would do, but also what's the quantum limit. I'm compensating for our measurement efficiency because we don't have perfect efficiency. But you see that sort of compensating for that efficiency, adaptive detection is getting much, much closer to the quantum limit. So this is really the best that your system could do, given that some amount of the photon is lost before you get to measure it all. And to contrast, another thing we did is we take our measurement record and apply the same trajectory to a further record. So what do I mean by that? What I mean is that if we're curious about whether or not it's the dynamics of the measurement axis or the correlation between the measurement axis and the state that matters, what we can do is we can say, okay, suppose that I take some particular phi of t, so some particular change of the measurement basis, and I just apply that to the next trajectory. So now I'm going to move the measurement axis in exactly the same way as adaptive detection, but the motion of the measurement axis is going to have nothing to do with the actual measurement outcome. And you see that that basically performs the same as heterodyne detection, maybe a little bit worse. So that's a sign that it's the correlation between your measurement, your back action, and your actual state that's giving you this advantage. And conversely, if we look at the absolute value of this quantity, that's essentially telling us what we're learning about photon number or this undesired information, whatever it might be. And you see that for heterodyne detection in this replay trick, we get essentially the same distribution of this, and it's pretty wide. But when we look at adaptive detection, this distribution is substantially narrower, which indicates that we're not really learning the undesired information. So with that, that was the experimental portion of the talk for adaptive measurement. I do want to come back a little bit to adaptive measurement at the end. But now I want to turn over to sort of look to future experiments and say, what are other capabilities that we can get from these high-efficiency amplifiers and from doing quantum feedback? So first I want to talk just about a general method that we've developed for strategically finding quantum feedback protocols. And I want to keep this, well, first I want to motivate a little bit more about using measurement for feedback. So to be a little more specific, one reason that measurement is really important in quantum mechanics is it gives us the nonlinearity. So you might hope that's sort of expanding the amount of control you could have in your system. The problem with measurement, of course, is it's intrinsically random. So if you want to use it for control, you're not going to get to choose what happens if you just projectively measure. But nevertheless, this shouldn't deter us, and certainly measurement is extremely important for preparing states, not only just for heralded preparation, but also for preparing entangled states. It's kind of the standard way to prepare remote entanglement in quantum systems, and it's also one of the standard ways to make spin squeezing, which is useful for atomic clocks. Both of these things are intrinsically random, and so the question I want to consider is, can we use quantum feedback to sort of get the best of both worlds, and can we sort of tame that measurement back action to get something deterministic? So to look at that problem in a pretty general context, suppose that we have some initial quantum state psi, or it could be a mixed state in general, and our goal is to prepare some target state. And this is just some abstract drawing of Hilbert space. My resources I'm going to allow myself are any measurement operator to keep things general. That's going to give us some random back action. And then some unitary control. So I'll have the ability to apply some Hamiltonian with some arbitrary rotation. And sort of the naive cost function you might write down is the fidelity. Just say, I suppose I want to just, at every time step, every time I acquire a little bit of information about the state, I want to choose my feedback unitary so that the fidelity is maximized at every time step. And unfortunately, this maximization isn't going to have a closed form expression in general. However, there's some pretty general approximations that you can make that let you do a lot better. So if you assume that at every time step we're applying this optimal rotation, then after doing one round of measurement and feedback, the fidelity as a function of that rotation angle is going to be maximal at 0. And that means that if you change your state a little bit due to the measurement, then this distribution is only going to change to order d rho. And in typical cases, that means that the optimal measurement, the optimal rotation, is also going to be order d rho. So your optimal rotation after doing a measurement will just be this tiny increment here. And when you make that assumption, then you can actually determine a closed form expression for the locally optimal feedback protocol. So don't worry too much about all the terms in here, but the important thing to take away is that this is just a function of the feedback Hamiltonian, the measurement operator, that should be an m, excuse me, not a y, and the state at a given time. And we haven't made any assumptions about the actual form of the system at this point. So now we have something that's very easy to simulate numerically, and we can plug in a lot of operators and just see what we can get from it. The first thing you might do is ask, how general is this? And I think one sign that it's pretty general is we can rederive a lot of the well-known feedback protocols. These are just the ones that I've tried. If there's any other ones you know of, let me know. I'd be curious to see if it applies. But for example, if we just plug in the measurement being the spontaneous decay operator for an atom, like in the previous part of my talk, and if we work in the measurement frame of say, a measurement of this operator, and we say that our feedback control is changing that measurement basis, so rotating around the sigma z axis, then you can derive the adaptive phase measurement protocol from the previous talk of the slide. So that's kind of nice. You plug in different operators and you can derive sort of this rapid purification feedback protocol for preparing a qubit state rapidly, some of these entanglement states. And then we also applied it to some new things. So what I want to mostly focus on is preparation of DICKE states using this measurement operator. But there's also some other things that we've developed that I can tell you about offline if you're curious. So entanglement, it's a useful thing to get with measurement. I'm not going to be talking about these extremely remote schemes. So for example, this is from that famous loophole-free Bell's inequality violation paper where they entangled qubits that were over 1 kilometer apart. And that's certainly not the regime in which I hope this kind of feedback to be useful because your feedback delay is very large. What we're more interested in are sort of these local systems where maybe you have some quantum modules that are necessarily separated by some more modest distance, feet or meters or something like that instead of kilometers. And this is going to be really important for superconducting circuits where you just can't put 1 million qubits on a single chip. All right, so the measurement operator we're after is this one here. So we're just considering any system where you can measure the total angular momentum of your system. So in superconducting circuits, you might do this by having a long transmission line where a signal would couple individually to qubits that are localized in different regions. This is also relevant to cold atoms experiments. So any system where you have a bunch of atoms coupled to a cavity and they're dispersively coupled, like in Younghung's talk, for example, this is a system in which you can very naturally measure in this basis. And the neat thing about this basis is that the DICKE states are eigenstates. So if you prepare your system in a separable state initially, and then you measure in this basis, there's a chance that you might project into sort of half the atoms being up and half the atoms being down, but a superposition of all of those, so that's entangled, and that's spin squeezing. Now I'm talking about a system with a large number of atoms. So even if we can develop a feedback protocol, it might not be that useful if that feedback protocol requires computing the time evolution of the stochastic master equation at every single infinitesimal time step. That might be possible for 2 or 3 qubits, but if you're hoping to do this for, say, hundreds or even millions of atoms, it's really not something I would want to ask my experimental half to do. So before I consider this problem in full generality, I want to say, is there a way that we can avoid having to do this really hard problem? Can we make theorists do some of the work? So the solution that we like using for this is this thing we call average sense optimality. Basically, we're just going to try to force our feedback protocol to be Markovian. The problem, as I've described, is that the number of possible measurement outcomes, possible states you can explore, just grows exponentially at every time step. You might do some measurement, some feedback, and then you do more measurement, more feedback, and the number of possible things you could reach here, there's no way you can possibly enumerate everything. So what you can do instead is you can assume that your feedback controller only has a short memory, which, as you remember, is basically the Markov approximation. You're going to assume that your feedback controller doesn't, at this time step, it doesn't remember what measurement outcome happened here or here or here. And so that, mathematically, that just corresponds to taking all of the density matrices you achieve after measuring and doing feedback and just averaging them and then spitting out a function rho bar. And the nice thing about that is not only is it physical, but it gives you a state that evolves deterministically. So whereas here, the state at a function of time depends on the full measurement record, here the state as a function of time only depends on some deterministic function of time that a theorist can just compute and hand it to the experimentalist and the most recent measurement outcome. So it's intrinsically Markovian. I meant to remove that slide. So now let's apply this to DICKE state preparation. So remember, we have this measurement operator. Our feedback operator is just going to be, I should have written it here, it's basically just this operator, but replace sigma z with sigma y. So we're just going to do global rotations on all of the qubits. It's symmetric. We don't have to do different operations on different qubits. And if you use that expression that I derived a couple slides ago, you can actually compute the optimal sort of proportional feedback coefficient. So this is how your measurement, how your rotation operation should depend on your measurement outcome. And then there's also some deterministic Hamiltonian that you should add. So you should basically add like a time-dependent Hamiltonian to your system. I plotted the amplitude of these rotations as a function of time for a specific operation. And you see that we can achieve DICKE state preparations in excess of 95% fidelity for a really wide range of the parameter space. I should emphasize this problem has been explored by a previous paper by Mabuchi that I referenced a few slides ago. But their protocol was intrinsically non-Markovian, and so it requires a sort of exponential blow-up in your feedback computational resources. Whereas here, we're enforcing the protocol to be Markovian, which is a severe constraint on what your feedback controller can actually do. But despite this constraint, you're still getting really high fidelities. So I'm plotting the fidelity of our state preparation as a function of the number of qubits going up to 50, and as a function of the number of excitations in that wave function. So this is the entire parameter space, and it stays above 95%, which is pretty nice. To zoom in on some of those specific details, if you look at the fidelity as a function of excitation number, it's harder to prepare W states. So these are states where, say, you have 50 qubits, or in this case 48 qubits, and you want an equal superposition of all states with exactly one excitation. So that's a pretty hard state to get if you're trying to do spin squeezing, because if you just prepare yourself in a separable state and projectively measure, the vast majority of the time you're not going to have exactly one excitation. But with feedback, you can almost deterministically prepare that. And as you increase the number of qubits that you put in that state, we can even go up to 100, and it's to be honest, it's a bit hard to tell if this is going to eventually converge to 0 or converge to something finite. But in any case, for pretty large numbers of atoms, we have a feedback protocol that works exquisitely well, I think. So it looks like I still have a bit more time. So with the last couple minutes, I'll talk about one more feedback protocol using the same kind of formalism, same kind of system. But now we're going to try to prepare something even harder, which is a GHZ state. So that's our target state. And particularly if you imagine trying to measure these local operators, this is an even harder state to prepare because these states are in a sense sort of maximally distinct from each other. So how do you make a measurement that's not able to just project you into either this state or this state? One way you can imagine doing this is try to enforce that every pair of qubits has the same state. So you want to make sure that each pair is in either in GG or EE. This is kind of a half parity measurement. To get something you can do locally or still have it be feasible for weakly interacting systems, you want to make sure that your measurement operator is sort of one body. And that's a pretty hard constraint because now you can't just do a parity measurement, which gives you entanglement no matter what the measurement outcome is. And these measurements are still going to very well distinguish these states. So if even a single, so I'm going to measure Zi minus Zj for all pairs of atoms in the system. And if even a single one of these measurement outcomes is not 0, then that means one of these systems has been projected into GE or EG. And that means that we basically dephase our whole system. So if you learn a tiny bit of information about the state, you collapse it completely. So this is going to be pretty hard for measurement-based control. However, we still find that we're able to get a significant enhancement in the preparation fidelity. So if we prepare the system in some initially separable state, which is the constraint that we enforce ourselves. I've only gone up to 8 qubits because it's a bit, well, we can make a symmetry reduction. We just haven't done that yet. But you see that for 8 qubits, the state that has maximal overlap with the GHZ state has a very, very low fidelity. So that means your success probability, if you were just going to do projective measurements, is pretty low. But with feedback, by the end, you can get well over a half. So even though you're not getting perfect fidelity, you're getting a massive enhancement in the success with which you can prepare a GHZ state. An interesting thing about these problems, and this is sort of getting more towards the conclusion of my talk, is that for the n equals 2 and n equals 3 cases, you see that the purity as a function of time remains 1. This is something that kind of comes up every once in a while in these feedback protocols. What means is happening is that even though your measurement operator is some complicated non-local thing, and your feedback Hamiltonian is local, so it's only acting on single bodies, you're actually able to exactly cancel the noise of your measurement with your feedback operation. So this is the purity not of the individual trajectories, but of sort of that ensemble state that I talked about earlier. So that means that no matter what your measurement outcome is, your feedback takes you back to the exact same state as a function of time. So you can write down conditions when in general this might happen. Basically have to solve this eigenvalue equation. But this is really just a condition for a specific state to satisfy the property that you can cancel the measurement noise with the feedback operation. And it doesn't really give you an intuitive sense of why does this happen for n equals 2 and n equals 3, but not n equals 8. And I think there's some interesting mathematical structure in these kinds of problems that would be an interesting direction for future exploration. So to conclude, looks like I'm a little ahead of time, but I think given that I'm the last talk, I won't feel too bad about that. Make sure we get out in time for the game. The adaptive measurements were the first part of the talk, where we try to see if we can change our measurement basis, conditional on some measurement outcomes. What new capabilities does that give us? And then secondly, talked about these more general schemes for deriving feedback protocols. And the questions that I want to finish with are the following. First of all is, can we come up with general conditions under which these feedback protocols are going to work? So, you saw that for n equals 2, we had some really good behavior. For n equals 3, sometimes it worked. But as you go up in excitation number, at least the measurement operators that we chose won't give you perfect fidelity. And I'd say that at this point, we don't have a good understanding of sort of when it's going to behave well and when it's going to behave less well. And also, what's the more general algebraic structure of when you get this perfect measurement cancellation property? And then sort of linking the two parts of the talk. This is not contrived. This is something that I think is something I'd like to explore with future research, is can you turn adaptive measurement into a control problem? And I'm sure there's been some work on this. But my sense is that there's no general formalism where you can say, suppose I want to measure this POVM. I want my measurement operators to only be in this set. How should I change my measurement basis in order to achieve that? And so we have some general methods for state preparation. And I think it'd be interesting to see if we can turn those methods around and see about using them for POVM generation. And with that, I want to thank everyone I've worked with on these projects over the years. So on the experimental side, I've worked with Irfan Siddiqui and his really incredible group at UC Berkeley, in particular William Livingston and Emmanuel Ferrand, who's now at Leigh, and Sheikh Cohen-Gorgi, who's now at the Technion in Israel, for a lot of really good discussions, and in Will's case, some really hard work in getting that experiment up and running. And on the theory side, Brigitte Whaley, and in particular Song Zhang, who did a lot of work on the second half of the talk that I told you about. And with that, I'd like to thank you for the time and for the great talks.
Okay, thanks. Questions?
So it seems that, you've done a single-shot phase measurement. So it seems like you could detect the phase, for example, of a squeeze states, and that would make compatible the use of squeeze states with the usual dispersive readouts of superconducting qubits. Is it something that you've thought about, or?
Oh, so you're saying like using squeeze states and adaptive measurement to read out
a superconducting qubits in the Z basis, for example?
I think it's an interesting direction. I think we wouldn't have the first system that might be interesting for looking at that. Like Hideo's project from 2002 looked at doing adaptive measurements for coherent state discrimination. I think there's one other paper that I should have put up there for trying to discriminate squeeze states with different phases with the explicit goal of trying to optimize qubit readout. So I think whether or not it's practical is an interesting question. I'm not sure I could say that off the top of my head, but it's an interesting way to look at it.
Okay. Any more questions?
Thank you for the talk. I was wondering about this optimality in the average sense. If I'm not wrong, you did not compare that to what you would have if you keep the full state running. Do you have an idea how much you lose by taking this optimality in the average sense?
Yeah, so just the GHZ results are pretty new, so we haven't tried that yet. For the DICKE states, that's essentially what Hideo did in his paper from a few years ago, and we reproduced those results. And there you're able to converge to unit fidelity. So it does seem like the averaging is what's causing your fidelity to decrease there. For the GHZ states, for the example that I showed, we haven't done that yet, but there are some other examples where we just do sort of a one-body operator instead of doing measurement operators. And there it seems like even if you allow yourself to use the full information, it really just doesn't converge. Like you have to run for a long time to get a unit perfect state preparation.
So in terms of end result, it would be very comparable, you say? You don't really lose?
For the DICKE states and for the DICKE states at least, it's very close. That's why you're seeing like 95% fidelity, which I think is useful experimentally.
Okay, Howard.
Very nice, thank you. I'll have to look at your QST paper, I guess. But maybe you could just briefly clarify, have you really got some very crude new filter for getting rho from which is somehow a Markovian? Yeah, I guess I just didn't understand exactly how you're turning into a Markovian. I mean, is it like you're estimating rho from one time step and then putting that into the formula that the sort of optimal formula and calculating things that way, or no?
Right. So there's two different cases for that. One is, well, maybe I shouldn't go back to that, but you can use the totally general filter with those equations that I showed you, and that will work. That will, in principle, give you a good protocol. For the results that I showed in the second half of the talk, we're using the exact filter, but we're just applying this averaging. So we're just feeding in rho bar instead of rho to those equations that I showed a couple slides ago. Does that answer your question?
I'm not quite sure what it means, but so you're also using it. Because DW of course also requires knowledge of rho, so you're using it for that as well. Yeah. So I need to go back. DW. So after you have rho bar, you say I have rho bar. I do one measurement that gives me some random noise on the average state, and so that's your optimal thing depends explicitly on dW at the current time step and then implicitly on dW at the previous time steps through the dependence of rho on the previous time steps. So if you do this average sense optimality, you only depend on dW. If you do the general optimality, then you depend on dW of t and implicitly on all previous. No, but I guess my point is that dW is not a directly experimentally accessible.
Oh, yeah. So in that case, because in this average sense optimality, you can compute rho bar of time, you can compute the expectation value at all times, and then you can, there's no additional experimental complexity with extracting dW from dV.
Okay. Maybe, I'd like to talk about it.
Sure.
It's okay, I'm going that way. Right, Matja.
I think it's also maybe related to Howard's question.
Okay.
So I think there is, you compare these two situations of using the full rho or rho bar, the average rho. Mm-hmm. So in Hideo's papers, and we did actually a paper with Ramon van Handel afterwards, so we considered actually the full rho, but the problem that we were looking was really a stabilization of a DICKE state, not generation. So I think there is the difference here is that for these average dynamics, the average rho, usually for this A of t's, you need to know your initial state, and even you change your initial state, you don't get to that final state. Whereas I think in all these other problem papers by John Stockton and in the paper with Ramon van Handel, we're really interested in having a stabilization protocol.
Interesting. Okay, so maybe I misread that a little bit then. So we assume that you know the initial state here because it tends to be pretty easy to prepare inseparable states. This formalism all works with mixed states, and in some of my previous work, we've actually put in mixed states.
If you change it, what happens? Do you have to rework the protocol?
You have to recompute this like A of t as a function of time. But that's something your experimentalist would say, what's the initial state? The theorist would compute these functions and then give it to the experimentalist. Maybe I'm still not quite answering the question. I'm happy to talk after, if you'd like.
Okay. Any more questions?
A precise question is about the formula that you have on the previous slide. So if you have a denominator in your feedback scheme, you see here.
Yes.
What's happened if rho commute with h of f? If the denominator is 0, what's going on?
Yeah, so that's a case where your feedback doesn't do anything to the state at all. So in that case, that's sort of a special case where you could choose to apply this rotation, but it's not going to do anything.
Okay.
So don't use this equation and just set theta to 0.
Okay.
Okay. If anyone wants to sneak out to match, I probably shouldn't have to say this. You have permission. Probably already done so. Any last questions, comments? Okay.
I'll be quick. You're asking if anyone's looked at adaptive measurement as a control problem. Mm-hmm. So I think you should look at the work by Ramon van Handel and Luc Bouten. So I referred to, they have this paper on separation principle of control. And so they do this kind of formulation. I cited them in my talk yesterday, but you might want to have a look at that.
Yeah, okay, I'll get that reference for you. Thanks.
Is that really about adaptive measurement?
They do where you can change the theta when you do a homodynamic detection based on your measurement record. Okay. Yeah, they do.
Yeah.
Okay, cool. Great.
Okay, I think that about wraps it up. Let's thank the speaker and all the speakers in the session.